Okay, so last theorem of the class is the Friendship Theorem. Nice way to end the semester, I think. So this one has a cool proof. So the first half of the proof will be graph theory, some pretty basic ideas in graph theory. The second half will be linear algebra, which we've used a little bit in this class early on, like for the matrix tree theorem, for instance. This will be a little bit easier strategy with linear algebra, but I'm going to gloss over some of the details. I don't know how many of us have actually had a course in linear algebra. Those that have, the details I skip should be easy to fill in. Those that haven't, we'll just have to take certain parts for granted, some computations we make. It shouldn't really affect anything in terms of completing the proof though, okay? All right, so let's let G be I'm for once gonna say finite graph. I'll talk for a moment about why I said that here. With the following property. Every pair of vertices, adjacent or not, just any pair of vertices, have exactly one neighbor in common. Okay, have exactly one common neighbor. Okay, so like if I grab two vertices, there's one other vertex like that between the two of them. This situation, for instance, is not allowed, right? You can't have two common neighbors. Okay. Even if the two vertices are joined, then they have one common neighbor here. Actually, all these guys together are sort of like set now. They can have other neighbors, right? You can have this vertex, there can be other edges coming out from them. They just don't share. Okay, so exactly one common neighbor. That's what my graph G looks like. Then G has a vertex, I don't know, well, let's not name it, adjacent to every other vertex. Okay. Sometimes we call such a vertex a universal vertex. Okay, so if you have this condition that every two vertices have exactly one neighbor, exactly one common neighbor, excuse me, then you have a vertex that's adjacent to every other vertex. Okay, so that's the, this, I don't know actually precisely why you would call this the friendship theorem. Every two people have a common friend, then there's someone that's friends with everyone. Actually, that's kind of an interesting emergent property, right? Sort of a bit surprising. And actually, this implies something further. Thus, we actually know even more that this graph looks like one specific way. Okay, so there is a universal vertex. Let's draw it here, and it's adjacent to everything else in the graph. Okay, so it's adjacent to everything, and then go ahead and like take a look at what this means about the rest of the graph. We can actually figure out even more about it here. So this vertex and this vertex, for instance, should have a common neighbor, right, by the property. Well, that common neighbor is one of these other vertices around the outside, because literally every vertex is pictured in this graph now because of the universal vertex. That's this one here. So, without loss of generality, we can just say it's adjacent to that one there, right? Just if it's not, just move it close. And so this one and this one have a common neighbor, exactly one, and it's this guy over here, right? That's sort of symmetric around here. We even saw this triangle thing kind of like tells you that these all three pairwise common neighbors are the third. Okay, and then these two out here also have a common neighbor, but that's the central vertex that's already been identified. So I can repeat that argument and say, hey, this one has a common neighbor with this one. They have a common neighbor. It's neither of these two, right? Because if it were that, I mean, so if we had this thing here, then this one and this one would have two common neighbors, right? This and this. So it's not that. So this one has some other vertex who's a common neighbor, and it's got to be that one there. And then we can continue doing this argument, and we get this windmill graph. So if you have a universal vertex and this property, you get this graph G no matter what. So thus G looks like this one here. Of course, there can be a lot more spokes to the windmill here, okay? But actually, it's interesting. For instance, it's never stated here, but this immediately tells us the number of vertices is odd. That just comes out for free with this property. kind of cool. So just this really simple property. Every pair of vertices have exactly one common neighbor gives rise to this property, which gives rise to this exact picture here. And this is called the windmill graph or the friendship graph. Okay, so I said finite graphs. This doesn't actually hold for infinite graphs. It's kind of interesting. So what is an infinite graph? I don't want to go through too many details here, but let's just think for a second here. Let me show you why it doesn't hold for infinite graphs. Okay, so for infinite graphs, so what's an infinite graph? For our purposes here, an infinite graph just means a graph with a countable number of vertices. Okay, so the best way to visualize an infinite graph with countable number of vertices is describe it by, you can always add another vertex to it. Like you can just keep adding vertices to it forever, and it goes on forever. So here's one example. You can start with a 5 cycle. And then what's the property? Every pair of vertices have exactly one common neighbor. Well, so far, no vertices have that property. And so what I'm going to do is just for every pair of vertices that don't yet have a common neighbor, add a vertex to the graph and make it the common neighbor of those two. Okay, so now these two vertices satisfy the property, but like say these two don't. So I add this one here. These two still don't, so add this one here. And just keep doing this forever. As I introduce new vertices, I'm getting new pairs of vertices that don't have a common neighbor, so I have to add even more vertices. So like obviously this thing's not going to terminate. And this theorem proves that it doesn't somehow like magically go back in on itself and become finite. Like that's impossible. But we can just keep adding forever. I mean, it just completely gets out of hand. But this will satisfy the exactly one common neighbor in common. And it won't have a universal vertex. Maybe that requires a little bit of thought, but I think it's pretty evident. You keep building like this. No vertex is adjacent to everything in this picture, at all. Okay. So for infinite graphs, it does not hold, okay, which is of some interest as well. Okay, so let's prove the friendship theorem. Okay, so proof of the friendship theorem, not of this infinite business. All right, so it's by contradiction. We'll suppose the theorem's false and let G be a counterexample. Okay, so let G be a counterexample. Okay, so what does that mean? G has the common neighbor property, but it doesn't have a universal vertex. Okay, so let me just write that out. Why not? I.e., each pair of vertices in G has exactly one common neighbor, but no universal vertex. And we're going to arrive at some kind of contradiction. It's going to be a rather arcane contradiction at the end. This proof will in no way be illuminating why it's true, as is often the case in contradictive proofs, but this one I would say especially so, which has a certain charm to it as well, of course, right? So, okay, so let's make the first observation, which we've actually already kind of illustrated above. So the first observation, this first property about it, is that G has no 4 cycles. Okay, it has no cycle of length 4. That follows from the common neighbor property, right? So take 2 vertices. So let's say otherwise, take 2 vertices U and V, and let me draw in blue here, like a dotted edge with a question mark. Maybe there's an edge between them, maybe not. It doesn't matter whether there's an edge or not. And imagine they have more than one common neighbor. Sorry, imagine they have a C4 on them, right? They're in the middle of a C4. I've drawn it this way. Maybe, I don't know, maybe it's not best to draw it this way. So if you have a C4, so C4 is a cycle of length 4, then the 2 middle vertices, 2 opposite vertices, U and V, or X and Y if you like, have 2 common neighbors. I mean, that's exactly what a C4 is. Actually, in disguise, this picture is easier to see. It's a cycle of length 4 is a complete bipartite graph with 4 vertices, 2 on each side. It's the same graph. And that's literally saying I have 2 vertices, whether or not they're joined by an edge, with 2 common neighbors. That's impossible, okay? So this follows immediately from that common neighbor property. Okay, and we'll use that a couple of times. Well, mostly just in the next part here. Okay. All right, so now using that, we're going to prove the following claim. This is a little more involved, that G is a regular graph. So all degrees equal in a regular graph. Okay, remember, what we're trying to prove is not regular, but that's not an issue because G is a counterexample, right? We're working with a graph that doesn't satisfy this property, and we're going to argue somehow that it's regular, and that, I mean, that's not a contradiction yet at all. That's just this counterexample to the theorem is regular. Interesting. I have no idea where we're going to use this property. It's one of those things you go through the details of the proof, and I don't know. Let's keep it in mind. We ought to use it, right? We ought to use it, but I actually don't know where it's going to come up. All right. All right. So let's prove the claim that it's a regular graph real quick. Okay. So let's start with proof with non-adjacent vertices U and V. Okay. Are we using the universal property here that these even exist? Yeah. For instance, right? I mean, the graph could be complete, and then there'd be no pair of non-adjacent vertices. But complete graphs have universal vertices. Every single vertex is universal. I think I'm back. Yes. So via no universal. So maybe that's where we're using it. Certainly we're using it here. I mean, let's see here. So yeah, on the other hand, I mean, this also follows from the one common neighbor property as well, right? I mean, if you can't have a complete graph if you have exactly one common neighbor, unless the number of vertices is like 3, right? So, but let's say this no universal vertex for now, but it should come up elsewhere, or exactly one common neighbor. Okay, so we take 2 non-adjacent vertices, and let me illustrate here and sort of explain along the way. So here's U and here's V. There's no edge between them. And let's look at U's neighbors. So U has neighbor W1, W2, W3. I'm going to put 4 of these, W4, and then WK. Okay, so the degree of U is K. There's K vertices here. Okay, and then I know like a whole list of properties here. I know that U and V have common neighbor, right? I don't know. I made that word up now. Say, so they have a common neighbor. Let's say it's W2. Okay, there's a slight reason for calling it W2 instead of W1. So why is it one of the W's? Well, all of U's neighbors are these guys here. So a common neighbor has to be among the neighbors of U. So, and V and U have exactly one common neighbor. So V sends an edge right to there. Okay. Now notice that V doesn't send an edge to any of the other WIs. That either gets us C4, right, a cycle, or you see that it violates the common neighbor property. So either of those are out. Okay. And then we look at W2 and U have a co-neighbor. Say that's W1. Okay, I'm still looking at U and W2. They're adjacent to each other, but that's fine. They also should have a common neighbor. Okay, that common neighbor is definitely among the WIs again, because those are the neighbors of U. And that could be anything. Let's say that it's W1 up there. So we've got this triangle here. Okay, and now let's notice, what do we want to notice here? There's a few things to notice here. Okay, so yeah, we did notice that V not adjacent to any WI for I not equal to 2. Right, otherwise we get a cycle. And also, but, oh yeah, okay. Let's also no wi and wj have a common neighbor other than u. So let me draw both these things that I'm claiming real quick. So such an edge doesn't exist, right? We already established that. The other type of edges that don't exist are, there's no other, vertex out here that's adjacent to W3 and W4 either, even aside from V, right? This can't happen either, because these two, again, W3, W4 would have U, and this thing is a common neighbor, or we'd have a cycle. Either of those are bad. So those are the two things that I've established here. That doesn't happen, and that doesn't happen. But V and WI, for I at least 2, have a common neighbor. Okay. So let's see here. Yeah. So why did I say I at least 2 here? V and W1 do have a common neighbor. That's W2, right? That's already drawn in the picture. But then if I look at V and W2, V and W3, V and W4, V and WK, each of those two have a common neighbor. Right? Let me draw on the first one. So W3 and V have some common neighbor. No, let's say W2 and V have some common neighbor. Okay, let's call this Z2 for now. All right. Z2 is not any of the WIs because V doesn't go to them again. And then, so I've got this new vertex Z. And then W3 and V also have a common neighbor. And I'm going to call this Z3. And that's not one of the WIs. And it can't be Z2 either, because if it's Z2, then W3 goes to Z2. And that would violate this condition here. So then I can keep arguing like this. Z4, ... and then V has a neighbor down here, ZK. Okay, and then we can pretend this W2 equals Z1, like if you just want to give a name to the neighbors. And then I found K neighbors of V. What does this then prove? So the degree of V is greater than or equal to the degree of U. Right? I illustrated a vertex Z that's adjacent to V. I found K of them, and there were K adjacent to U. Okay, but by symmetry, so it's symmetric argument, we can argue the same thing, that D of U is greater than or equal to D of V. Right? Just repeat the argument, start with V and its neighbors, and then produce neighbors of U in the exact way that we produce the neighbors of V, which would give us that DU is greater than or equal to DV. So these two things together say that DU equals DV. Right? Okay, so what does this mean? It means that if I grab a vertex U, everything that's not adjacent to U has the same degree as U, right? V is arbitrary. But that doesn't quite yet prove the graph is regular. There's still a couple more steps to do. Okay. Yeah, how do we prove that? Oh, yeah, okay. My computer wants to update, of course. Go away. Okay, so now, yeah, as of this point, U and V have the same degree, and anything not adjacent to U has the same degree as U. Moreover, everything not adjacent to V has the same degree as V. Okay, but now observe that every vertex except W2 is not adjacent to U or V. One or the other, right? Because they have exactly one common neighbor. There's no other vertex adjacent to both U and V simultaneously. So every other vertex is non-adjacent to one or the other, and therefore has the same degree as the one that it's not adjacent to. Okay, so that means every vertex except for possibly W2 has the same degree, K, right? So so let's say every vertex, what's the letter we haven't used yet? We didn't use X's, right? Yeah, every vertex X except W2 is not adjacent to, so D of X equals, let's just call it K, right? We named it K here. So it's not specifically equal to DU or DV, it's one or the other. And then we have to examine W2. Oh yeah, but that's easy. So d of x equals k, but, and so for what, yeah, so what about, let's write it this way. What about W2? Here we use universal vertex, finally. W2 is not universal. Right? It's not universal. So there's a vertex to which it's not adjacent. Right? There's a y that it's not adjacent to. What's the degree of y though? D of y equals k, because k was either not adjacent to u or not adjacent to v, just like we established everything was degree k. And now I have W2 and y not adjacent to each other, so they have the same degree as one another by repeating the argument above. And y has degree k, so W2 has degree k. Okay, so W2, degree of W2 equals k. Okay, yeah, so here we use the not universal property, like barely, right? I mean, like, but this came at the end, right? Because here's the thing to keep in mind, why we'd have to actually use it there, is I don't know anything about W2. It's one of the neighbors of U. In fact, it's the common neighbor between these two. But W2 in principle, without the non-universal property, maybe it's adjacent to everything else, right? In fact, if you take the windmill graph and take two non-adjacent vertices and look at their common neighbor, it's going to be the central vertex, which is universal, right? So like in the actual example, this would be universal. Okay, so there we use the property. That's a relief. Okay, so this proves the claim. Right? So that means G is regular. Every single vertex has the same degree. And actually, we only care about that for the vertices W1 through WK. So let's examine those again. Okay, so even though they're defined inside the claim, we can still talk about the WIs we want. Okay, so now let's sum the degrees of W1, W2 up to WK. Okay, so let me redraw this picture here. W1, W2, up to WK, and each of these has K edges coming out of them. And each of them has a common neighbor as well, right? Every pair of the WIs have a common neighbor, and that's actually U itself. Right? This is just the illustration from before there. Okay. So first, if we sum the degrees of these things, what do we get? This is a sanity check here. Can someone tell me what number do you get if you sum the degrees of these?
Degree of U squared? Or K squared?
K squared. Yeah, exactly. You get K squared, right? There's K of them, and each has degree K. So K squared is your sum. But notice this counts every vertex of G. Well, once, except for one vertex gets counted more than once. Okay, so every single vertex, except for U, let's see here, every vertex of G except U is counted once by this sum as we have exactly one common neighbor. One common neighbor among the WIs. Okay. So every single vertex, what am I saying here? So every single vertex should be counted once because why? Because if I take two of these guys here, they have a common neighbor. Is that what I want? That seems to count that one twice. No. Sorry, they don't have that. They specifically don't have this picture, because this creates the forbidden graph, the C4. So what does it mean? Why am I getting this quantity? I'm confused now. So I sum these guys. Every other vertex sends an edge to this set WI. Because every vertex with U has a common, so as we have exactly common one with U, right? So you take an arbitrary vertex X out here and U, they have exactly one common neighbor. That common neighbor is among the WIs and there's no repeat. So this edge vertex X is counted exactly once because of W1, and this vertex X is counted because of W7, and so on and so forth, okay? But U gets counted multiple times. How many times does U get counted? It gets counted K times when I add these up because there's like K edges going into it, right? So when I add these degrees, each of the outgoing edges is counted, and each vertex that is outside of the set gets counted once, okay? Moreover, even the WIs themselves get counted by this sum as well, right? Because again, U and W2 have a common neighbor, and that's among the WIs here, okay? So this means that, okay, and U is counted K times. So this means that the number of vertices, let's just write it like this. So the number of vertices of G, which is N, this equals K squared minus K plus 1, right? The sum of the degrees of these things is K squared. That K squared counts every single vertex one time, except for U, which gets counted K times. So in order to get the correct amount, I have to subtract off K minus 1 from K squared, okay? So minus K minus 1 is K plus, minus K plus 1, okay? So now I have more information about my counterexample, right? My counterexample is K regular and has exactly this many vertices in it, okay? Which is kind of an interesting thing, okay? All right, so now let's make what seems to be a small observation, which will lead to our contradiction in the second part of the proof here. Okay, so observe another observation here, that when K equals 1, then N equals, what do we get here? 1, right? So when K equals 1, when it's 1 regular, we get the graph of a single vertex. And this single vertex can't be our contradiction for one of two reasons. Either let's consider this as a windmill graph, or like this has this, vacuously has a universal vertex. It has the vertex adjacent to all other vertices. But I would prefer maybe to just state the theorem only for graphs that have it more than one vertex. Like that would be another thing. But the point is this, so
There's
let's
also
throw this
no
one out.
pair of vertices. So
Ethan,
every pair, there's
oh
also
yeah,
no pair of vertices, so every pair of vertices has a common neighbor.
right, yeah. So I mean, this definitely satisfies the condition of the theorem. Every pair of vertices has a common neighbor, and it has a universal vertex. So this is not a contradiction because it's actually a windmill graph, right? It's actually the friendship graph we desire. And then when K equals 2, this one's a little more interesting here. Then what do we get here? 4 minus 2 plus 1, we get N equals 3. And then, okay, so it has 3 vertices, but if it has 3 vertices, in order for it to satisfy the common neighbor condition, it has to have all 3 edges, right? But this has a universal vertex. It has 3 universal vertices. Okay, so this is not my contradiction either, right? So K is greater than 2. Okay, that's what we know now, that our contradiction is K regular, it has this many vertices, and that K is greater than 2, because K equals 1 and K equals 2 were not contradictions. They satisfied the theorem, okay? All right, so now we move on to the second part of the proof, which will conclude in the second part of proof that K equals 2, which contradicts K greater than 2. All right, that's the bit of arcana that I sort of mentioned there. All right, we could have also said that derive at K equals 2 and then draw this picture as the only example, and that would contradict the existence. Our counterexample would not be a counterexample. Okay, all right. So the second part of the proof is it's not difficult, but it does involve linear algebra. Okay, so consider the adjacency matrix A of G. I went back through the notes and we talked about incidence matrix and the Laplacian matrix, and I think it mentioned the adjacency matrix to you. But let me redefine it for you here. This is actually sort of amusing to me because many graph theory classes define the adjacency matrix on day 1, and we're managing to do it on the last day. Like it's sort of rare. So what is the adjacency matrix? It's really, really simple. So you have an n vertex graph. It's an n by n matrix indexed by the vertices v1, v2 up to vn. v1 up to vn. So this is A. And then let's say that, Aij. So entry ij equals 1 if and only if vi, vj is an edge. If they're adjacent to each other, right? And it equals 0 otherwise. Okay, so if it's not an edge. So it just records all the edges of the graph, right? I've indexed the vertices in rows and columns, then I look, is v1 adjacent to v2? If it is, I put a 1 there. Is v10 adjacent to v12? I put a 1 there, right? And notice, for one, this matrix is symmetric around the diagonal, because like v7 being adjacent to v10 is the same as saying v10 is adjacent to v7. So if I get a 1, here, I get a 1 here. If I get a 1 here, I get a 1 here. The diagonal is all zeros because a vertex is not adjacent to itself, okay? Notice, this isn't important for today's proof, that this matrix can easily encode multigraphs because multigraphs allow loops. Then that's like, oh, you can have ones on the diagonals. It can also encode multi-edges because then instead of putting a 1 here for them being adjacent, I'd put a 5 if there's 5 edges between the two of them. It can even encode directed graphs because then it wouldn't be symmetric anymore. It'd be like, oh, arc v1, v3 exists, but v3, v1 doesn't exist. So you'd mark, up here only and not down here. So this is a great way of encoding graphs for like a computer or to do linear algebra with, okay? For working with them in a proof in our class, it's not too useful because it's much harder to visualize like what's going on in this picture here, but certainly it encodes all the information that a graph does. Okay, is this definition clear for the adjacency matrix? This is the most natural way to encode information about a graph, right? It tells you all the number of edges, and you can derive interesting information here. What's the degree of v1? Well, it's the number of ones in the row corresponding to v1. It's that's the number of edges hitting it, or it'd be the number of ones in the column. You can take either one, right? What's the number of edges? Oh, it's just the sum of all the ones in here divided by 2, right? You can actually prove the handshaking lemma by that argument here as well. But there's other like really cool stuff you can do. If you take the adjacency matrix and square it, if you look at 2 vertices in the square of the adjacency matrix, I'm going to tell you this, but you can argue this yourself too. If you look at 2, okay, no, let me talk about the square here for real quick. So if you take the square and fill it in, and then look at, say the entry vi, vj, right? And you get some quantity here. It's not necessarily going to be a 1. You're going to get some quantity here. This will count the number of walks of length 2 from vi to vj. Okay, that's something that would need to be proved. It's not very hard to prove it, but so it counts the number of like common neighbors between the two of them actually, which is highly relevant to our theorem here. Okay, but this is just a linear algebra proof to prove that it counts the number of walks. It has to do with the fact that the 1 here counts the number of walks of length 1 from vi to vj, namely the number of paths from vi to vj. And when you take a square of it, it's the number of walks of length 2. When you take it to the 10th power, it's the number of walks of length 10. Now walks, not paths, they may repeat, and they may be cycles, for instance, okay? But when you have walks of length 2, they can only look like a path, right? Walks of length 2 can't repeat unless vi equals vj, and then you go out and come back, okay? So, but actually that tells us something here, okay? I'm gonna use that information. Some of the proofs of this are different, okay? So for us, okay, so I'm gonna just call this a theorem. A2 counts number walks of length 2 in G, okay? That's true in general. But for the graph we're talking about specifically, so let's call it for our A2. So thus, how does our A2 look like? So any 2 vertices in our graph, Vi and Vj, how many walks of length 2 do they have between them? If Vi is not equal to Vj. A walk of length 2 is like this.
1.
Yeah, they're exactly 1, right? So it's all ones here, all ones here. What if I look at Vi equals Vj? How many walks of length 1 does a vertex have back to itself? More than 1.
Degree?
Yeah, the degree, exactly. That's right. You can walk out along an edge, and then you have to walk back along that edge if you want to return to where you started. So there's 1 here, 1 here, 1 here, and so on. But I know the degrees of all my vertices. They're all k. So I have k's all the way down the diagonal. So that's my a there, okay? So I can get that via this theorem. There's another way to get this as well, okay? The other way to get this, let me just talk about that for a moment here. The other way to get it is to look at what a looks like. Well, what does a look like? Well, it's not as pretty as this one here, but what does a look like? Well, each column has k1s in it, right? Because that's the degree. And then if I look at 2 columns, they have exactly 1, 1 in the same row. That's because these correspond to having the same neighbor, okay? So you have this matrix that in each row and each column you have k1s, and in any 2 rows or in any 2 columns, they agree in 1s in exactly 1 position. If you take that matrix and square it, you will get this matrix here, okay? That's just a bit of linear algebra you can check. Like, that's a nice property, right? K1s in each row and column, and in 2 rows and columns like agree in 1 position. In terms of 1s, the square of that comes out to be this very beautiful matrix here. So you can argue it that way as well if you like. But this also just follows from this graph theory theorem here that you can prove. Okay, the proofs of those 2 arguments are well, I mean, this one's more general, but okay. So now we need to know the eigenvalues of this matrix, okay, which is maybe a little bit surprising. Okay, so we want eigenvalues. Actually, we want the eigenvalues of A. They have a certain meaning and certain properties, but we're going to derive them from the eigenvalues of A squared. Okay. Okay, I'll just say A squared first. Okay, so okay, if you haven't had linear algebra or haven't had it in a while or don't remember, what are the eigenvalues? So they're solutions to the following equation, AU, the real solutions to this equation here, where U is a non-zero vector, right? So I've got a matrix times a vector. This gives a vector, and I want to get back U scaled potentially by some quantity here. These U's here are the eigenvectors, and this chi here, which is a real number, is an eigenvalue, okay? These have a ton of importance in linear algebra, and especially in its applications in, well, there's a trillion examples you can look at. These things come up all the time, physics, computer graphics, and so on. They actually have a meaning in graph theory as well. And I think I've mentioned this before. There's a study of eigenvalues and of matrix properties of the adjacency matrix. This is called spectral graph theory, like understanding the properties of an adjacency matrix tell you things about the graphs. You, in fact, for instance, I think the chromatic number of a graph is always bounded above by the largest eigenvalue or something like that. So there's like these cool properties like that that relate to stuff we talked about in this class. Okay, for our purposes, the meaning of the eigenvalues are irrelevant. They don't mean anything to us today. They're just something we can compute, and they're going to give us a contradiction. Okay, so just keep in mind that in principle, like if you know enough linear algebra, you can solve this equation here for, you know, a given matrix A, and our given matrix, our given matrix here is A squared. So I want solutions to this equation for A squared, but A squared looks like this, which is a good matrix. Good matrices are easy to find eigenvalues of. Okay, this is something we've done. I'm not going to do the computation. I'm going to tell you what they are, but let's note that A squared can be written in the following way. What is A squared? It's just the all ones matrix, we usually denote as J, right? Plus K minus 1 times the identity matrix. That's the diagonal matrix, right? This is what this guy is. It's ones everywhere plus K minus 1 more added to the diagonal, right? We just decomposed it to that. Finding eigenvalues of a matrix in this form is super easy, okay? So eigenvalues are, what are the eigenvalues here? We get, what do we get? We get what? N K plus 1? No. Geez, I haven't done this in a while, but we get that with multiplicity. This is relevant actually, 1. And we get just K minus 1 with multiplicity k minus 1. No, not k minus 1, nonsense, n minus 1. There's as many eigenvalues here as the degree of the matrix here. Okay, so there's n of them. There's n minus 1 copies of k minus 1, and then 1 copy of this guy here. Okay, that's not that hard to see. Actually, this one certainly is easy. Okay, this quantity though, what's this quantity? This can be written in another form by something we derived in part 1 of the proof. N was related to k somehow, right? Yeah, exactly, Eric. This comes out to be exactly k squared, right? N was equal to k squared minus k plus 1. So n plus k minus 1 is k squared. Okay, that's going to be handy, right? Okay, so these are the eigenvalues. They can be easily computed. But what we really want is the eigenvalues of A. So want eigenvalues of A. You can't always do this, but in this case you can. What is your guess? If you have eigenvalues of A squared, what do you think are the eigenvalues of A? Or if you know, you can tell me as well. Anybody remember how to go from eigenvalues of the square of a matrix to the original? And if you don't know, care to wager a guess? They're the square root of the eigenvalues of the squared matrix. Okay, so they are, well, k squared square rooted is k. So there's k, and this has multiplicity 1 still. Multiplicity doesn't change. Now here's where things get interesting. The eigenvalues here are k minus 1. It's plus or minus root k minus 1, right? There's 2 possibilities here. Okay. So let me rewrite this way. So some of the eigenvalues are k minus 1, and some of them are negative root k minus 1. Okay. And this has multiplicity, say r, and this has multiplicity, say s. Like, I don't know what the multiplicities are. That I can't predict. Okay. But what can you tell me about r plus s at least? Yeah, it should be n minus 1. Good, Eric, right? The multiplicity should add up to the original multiplicity there. Okay. If we're lucky and we have something like this that you can just take the square root of, then you know exactly what it is. Okay. So these are the 3 types of eigenvalues of A. Okay. Now, anybody remember a property? What happens if I sum the eigenvalues? So if I sum the eigenvalues, I get k plus r times root k minus 1 plus s, let's say minus s times root k minus 1, right? That's the minus there. If I sum the eigenvalues, anybody remember what happens? This equals the trace of the matrix. Anybody remember what's the definition of the trace of the matrix? Anybody remember? Well, one definition is the sum of the eigenvalues, but what's the other definition? Yeah, it's the sum of the diagonal values of the matrix. Okay, sum of diagonal of A. The diagonal values of the matrix are not equal to the eigenvalues, though, in general, right? What's the sum of the diagonal values of the matrix A we're talking about, though? It's 0, right? It's the original adjacency matrix. It's all zeros. Okay, so now we have this nice equation then, and then we're nearly done. Oh, good, we're fine on time here. So this implies that k plus r root k minus 1 minus s root k minus 1 equals 0. Okay. So, for instance, r is not equal to s. Right? If r equals s, then this term cancels with this term, and then I get k equals 0. But we know k is not 0. Like, actually, we didn't technically. Wait, what? No, I'm just wondering. Did this even make sense up here? When k equals 1, we got n equals 1, but this is actually a 0 regular graph. So this is actually problematic anyway, right? We said the graph is k regular, and n has this many vertices. So this example didn't even make sense, right? But here we were okay, right? This graph had 3 vertices and was 2 regular. Anyway, it doesn't matter. We threw this one out regardless. I just realized it's wrong for another reason. Okay, let's go back. So yeah, r is not equal to s, otherwise k equals 0. which is definitely out. And then let's rewrite this as, I don't have it like that. I reverse the things here. I don't think it matters. R minus S times root K minus 1 can be written as equal to negative K, right? I just factor out R minus S from those things and move K to the other side. And then let's square both sides. I get R minus S, K minus 1. And then negative K squared is just K. I mean, negative K squared is just K squared. And now, here's where we're finally going to get a contradiction here. This equality implies K minus 1 divides K squared, right? K minus 1 times something equals K squared. So K squared is divisible by K minus 1. And this doesn't usually happen, okay? Right? When does this happen? This is a little bit of number theory. I'll leave you guys to maybe chew on this at the end, but it doesn't happen once K gets past 2, okay? But there's our contradiction. Remember, K had to be greater than 2. And now I just proved that K is at most 2 by this divisibility property here, which came from the computation of the eigenvalues. This is a contradiction. And so we do have a universal vertex, okay? Sorry, I'm looking at Eric's message here. If K equals 0, you get non-real eigenvalues. I see what you're saying. Yes. That's right, Eric. Yeah, absolutely. But yeah, obviously, you know, K, we should have stated from the start that K was definitely at least 1 here. Okay. All right, so that ends the proof. As I said, like it's not very illuminating in a sense, but I think it's pretty cool. It uses 2 different techniques entirely. Yeah, and again, when you have these nice, very symmetric graphs like that have properties, every 2 vertices have exactly 1 common neighbor, keep in the back in your mind, hey, wait a minute, that says a lot about my matrix, my adjacency matrix. It's going to be very, very nice. Nice adjacency matrices, or just nice matrices in general, we know a lot about them, right? Use linear algebra. Linear algebra has been developed over hundreds of years, much longer than graph theory. We know a lot of stuff about good matrices. So work on that when you have that. Regular graphs, great thing to apply adjacency matrices in linear algebra too. Yeah. Okay, good. So yeah, this is maybe what remains to be proved if you're not quite sure, but this is easy to check. Okay. All right, so that'll do it. That's the last class. So thanks everyone. It's been a pleasure. You know, despite the fact that we were online, I thought this went reasonably well, and I appreciate you guys sticking with it.